Hi everyone. Um, Before we start diving too deep into physics and the study of motion, we need to talk about vectors and scalars. In your study of physics and science so far, you've probably measured a variety of different things. And I would bet that all the things you've measured have been what we call scalars. So scalars are quantities that have only what we call magnitude. Magnitude is something that tells us how much of something there is. And a scalar is represented by, when we write a scalar down on paper, we do it with a number. And some units as well. So for example, you might have measured at some point the mass of something, which you would record using a number and units. So 70 kilograms. That's an example of a scalar. It just has magnitude, something that tells us how much mass is there, and it includes some units. You might have measured the distance of a variety of things. Maybe you measured something that was 25 centimeters long. That's another example of a scalar. Distance is a scalar. It just has this number and some units that tells us how much distance is there from one point to another. Another thing you might have measured could be time. You measured maybe how long it took something to happen. Maybe you measured something like 42 seconds. Okay, that's another example of a scalar. Now, what we're going to start measuring and looking at in physics is something called vectors. Vectors are something that have both magnitude, just like scalars do, but they also have a direction. A vector can be represented by a number, just like a scalar, but also a direction word. Or by an arrow. So in thinking of something that you might have come across that is inherently a vector, I kind of thought about wind speed or wind velocity. If you look up on the weather forecast what the wind is currently doing or what the wind's going to do tomorrow, it'll tell you the speed the wind is likely to be, maybe 30 kilometers per hour. But it'll also give you a direction, something like 30 kilometers an hour northeast. So this is a great example of a vector. To give someone wind velocity, you need to give them this first part, the magnitude, the part that tells them how much wind there is, and also the direction, the part that tells them where the wind is going or coming from. So this is an example of a vector that's written using a number and a direction word, 30 kilometers per hour, and then my direction word is northeast. But I said I can also represent this using an arrow. So I could say, if we say north is towards the top of my page, then northeast is kind of like that. So if I draw an arrow going that direction and I say the length of this arrow is 30 kilometers per hour, there's a great example of representing a vector using an arrow. Arrows are really convenient because arrows have a direction and a length, which is convenient for representing a vector because vectors have a direction and a magnitude. So we make the length of our arrow depend on the magnitude of the vector, and that works out really nicely. Now, up till now when you've been working with scalars, something you might do with them is you might add them together. If a person weighs 70 kilograms and they hold on to an object that weighs 20 kilograms, you might want to know the total mass. So you'd have to add those two scalars together. 70 kilograms plus 20 kilograms is 90 kilograms. We can add distances together, we can add times together. That's all fairly simple. If we want to use vectors, we're going to have to know how to add vectors together as well. And I'm going to walk you through how to do that. But rather than just give you the rules for adding vectors right away, I want to take a step back and think about how you would add numbers. Because it turns out the rules for adding vectors are really similar to the rules for adding numbers. So, let's look at this. How do you add numbers? Now this is going to seem like a little bit of a simple example here. I'm sure you all are great at adding numbers. You can do it very quickly in your head. My goal here is not to teach you how to add numbers. My goal is to take something you can already do very quickly and very easily and make you think about what the rules are for that thing. Because we don't always think about the rules for adding numbers when we do it. We just do it instinctively. It's second nature. So let's kind of slow down and think about the rules for adding numbers. The way I like to think of it is there are three basic rules for when we add numbers. We can put them in any order. For example, 1 plus 2 is the same as 2 plus 1. Each time we add a new number, we start where the last one left us. And the answer to a bunch of numbers being added together, which we might call the result, is counted from start to finish. Now these last 2 points maybe doesn't really seem maybe that obvious exactly what I'm trying to say here. So I'm going to demonstrate it with an example down here. So here are three numbers, 3, -2, and 1. And we're going to add them together. So what do I mean when I say each one starts where the last one left us? Well, first of all, let's do the first number, 3. And let's do this visually by looking at a number line. So the number 3 would be 1, 2, 3. Right here. Now I'm going to add another number to that. I'm going to add the number -2. So when I count my -2, this rule tells me I have to start where the last one left me. So I don't go back to the 0 and count -2. I don't start over here and count -2. I say, where did the last number leave me? That's here. Starting there, I'm going to go -2 or left 2. Okay. And now I'm going to add my final number, 1. Well, where do I start counting my 1? I don't go back to 0. I don't go from here. I don't go from here. I look at where the last number left me, which was here. And then I do my +1. Okay, so that's just a bunch of blue lines on a page. It's hard to see how that's really an answer. So let's look at the third rule. The result of adding a bunch of numbers is counted from start to finish. So where did I start? That was over here, where my blue line started. So there's my start. And where did I finish? Well, the last arrow brought me to here. So that's my finish. So from start to finish is 1, 2. So the answer to this question, 3 plus -2 plus 1, is 2. Now we didn't really look at the first rule, where I claimed we could put the numbers in any order. So let's go through that and just double check. Here I have the same 3 numbers, but in a different order. There's my 3, there's my -2, there's my 1. They're in reverse order. So I kind of illustrated this first addition in blue. Let's do this next one in red. Again, it's the same numbers, just in a different order. So let's start with the 1. Okay, then making sure I start where the last one left me. Over here, I'm going to do -2. And then, starting where the last one left me, over here, I'm going to do 3. Okay, so again, that's just a bunch of arrows going different ways. How do I find the actual result, the answer to this question? It's counted from start to finish. Well, again, I started right here, my first red line, the 0. And I finished over here, where my last arrowhead is. So from start to finish, goes from there to there, and that is 1, 2. So this answer is 2, which is the exact same as the answer I got using the blue method. So that sort of helps convince us that the first rule is true. When I'm adding numbers, I can put them in any order. Okay. So the reason I wanted to start with these really simple problems and kind of break them down and think about the rules, as I said before, is because the rules for adding vectors are very similar to the rules for adding numbers. So let's now look at vectors. Okay. Not only are these rules the same, they're basically identical. When we're adding vectors, we can put them in any order. Each time we add a new vector, we start where the last one left us. And the answer, in this case, the answer has a bit of a different word. For adding, I called it the result. Here I'm going to call it the resultant. The resultant. So there's this extra little bit. It's the word result with ANT on the end, called the resultant. And just like with adding numbers, it goes from start to finish. Okay, so basically the same rules. Let's use them to add some vectors. So here are 3 vectors, right? 5 meters per second right, 3 meters per second up, 4 meters per second down. Each of these has a magnitude and a direction. A magnitude that tells us how much, and a direction that tells us which way. A magnitude that tells us how much, and a direction that tells us which way. So let's draw the first one. We said before that vectors can be conveniently represented using an arrow. So let's draw these using arrows. Here they're given using a number and a direction word, which was one way we said we could do it, but let's go to the arrow way. So 5 meters per second right. Okay, there's an arrow that represents 5 meters per second to the right. And I'm going to add to that 3 meters per second up. So I'm going to draw an arrow that has a length of 3 instead of a length of 5. So it'll be shorter than this arrow, but not quite, but a little more than half its length, because 3 is a little more than half of 5. And this arrow is going to be going up. But where do I put this arrow? Well, remember, every time I add a new vector, I start where the last one left us. This guy left me here, so that's where I'm going to start my next vector. And it'll be 3 meters per second up. And then my final vector, 4 meters per second down, where do I put that? Again, I start where the last one left me, which is up here. Now, instead of drawing this exactly starting where this one left me, because that would have me basically retracing the exact same arrow, I'm going to draw it just a little over to the side, just so that it's easier for people to see that there is a new vector here. And this one has a length of 4, so it should be longer than the 3, but not quite as long as the 5. Okay, so there are my 3 vectors added together, each one starting where the last one left us. So what's the answer to this question? What's the resultant? Well, the resultant goes from start to finish. So I'm going to draw a vector, an arrow, that goes from the start to the finish. That is my answer. That is my resultant. Okay. Now again, let's just check this first rule. Let's check that it's actually okay to put them in any order. So let's, what order do I want to put them in? Let's do the 4 down, then the 5 right, then the 3 up. I'll do that over here. So this is another way of adding the same 3 vectors, starting with 4 down, then 5 right, 3, and then 3 up. Okay, so 4 down is like that, 4 meters per second. Then 5 right, starting where the last one left me. So this is 5. It's going to be a little bit longer than that 4 was. Good. And then 3 up. Okay, again, that just looks like a bunch of lines. What is my actual answer? What is my resultant? Well, it goes from start to finish. So let's check this. When I put them in a different order, did I get the same answer? Well, my answer is a vector. It has magnitude and direction. And if we kind of compare these two resultants, these two answers, I would say they have about the same magnitude, the same length, and the same direction. They're both going mostly to the right, but slightly down. So I got the same arrow regardless of which order I added these vectors in. Another way to remember this second rule, each one starting where the last one left us. You may have sometimes seen some photos of elephants hanging out in the jungle, especially if one of them is a baby elephant. The way they sometimes walk is sort of in a line, and one elephant will use its trunk to hold on to the tail of the elephant in front of it, especially if it's a baby behind and then a mother elephant in front. So when we're talking about arrows, we often call this the pointy part, the arrowhead, or the head of the arrow, and the opposite end we sometimes call the tail of the arrow. So my physics teacher told me that you always add vectors the way elephants walk in the jungle. Head to tail. Head to tail. So if that helps you remember it, think of it that way. You always add vectors the way elephants walk in the jungle. Head to tail. It's just another way of saying each one starts where the last one left us. Another thing I want to say here is sort of these units. I threw these in here just so we remembered what units were in the problem. But the way I draw this wouldn't change if these units were different. If these were all, instead of meters per second, if they were all newtons, I'd draw my picture exactly the same. I just write newtons here instead. If this was all meters per second squared instead of meters per second, again, I draw it the exact same way. I just write the units as meters per second squared. So the units doesn't really make a difference in how I draw the vectors. What's important is that the length of the vector represents the magnitude. So vectors with more magnitude, like this 5 over here, need to have more length. Okay, so before you guys go off and practice that, I want to talk to you in particular about two important types of vectors, two important vectors we'll look at in physics, and that is distance and displacement. Distance is for sure something you guys will have heard about and talked about and measured. Distance is how far something travels along the path it took. So let's say I trace out a path. Let's say I start over here and I go this direction 4 meters, and then I go this direction 3 meters, and then I go this direction 4 meters. Okay. What would be the distance I traveled? Well, I think you could probably look at this and say 4 plus 3 plus 4 is 11 meters. And what you're doing to find that is you're measuring how far this object traveled along the path it took. You're tracing out the whole path and you're saying how far was this leg, how far was this leg, how far was this leg, adding them all together. And 11 meters sounds normal as a distance. This is a magnitude. It has units. There's no direction. That's because distance is a scalar. We don't need to include a direction when we're talking about distance. But there's a very important quantity in physics called displacement. This is actually used in physics a lot more than distance is. So it's worth talking about it. Displacement is different in a couple of ways. One of the ways is that displacement is a vector. So it has magnitude and direction. Displacement is defined as the change in position, and I like to think of it as a straight arrow from start to finish. So here's a big difference. Distance depended on the path. Displacement does not depend on the path. It depends on the start and the finish. So if I want to know the displacement of this object, I don't actually care where it went. I don't care about this path. I just care about where it started and where it finished. And I want to draw a straight arrow from start to finish. So a straight arrow from start to finish looks like this. That would be my displacement. So that's how I would draw it. And how would I write it in words? Well, how long is this arrow? Because this thing looks like a rectangle, this arrow should be same length as that one. This should be 3 meters. And again, because displacement is a vector, I need to add a direction word. We could say 3 meters right. So not only is displacement different from distance in that it's a vector and not a scalar, it also can have a different magnitude. My distance was 11, which we measured along the path, and my displacement was 3 meters, which we measured just straight from start to finish, and it had a direction too, which was to the right. So hopefully that gives you a good sense of what the difference between a vector and a scalar is, how to do some simple math with vectors, how to add them, and how to draw them, and also a sense of the first two physics quantities. We're going to be talking about distance and displacement, how they're similar, and how they're different. Thanks for watching.